Okay, let's start. So good afternoon, everyone. Welcome to EIEG 4216, Design Methodology of Modern Digital Circuits. So the course will be available also online. So just in case that some of you get sick, you need to attend it online through Zoom. And the Zoom link has been posted in the Blackboard. So I'm a course teacher, I'm Professor K.P. Poon. So this is my office room number, Hosing Engineering Building, room 326. And this is my telephone number and my email address. So you can find me. If you want to contact me, you can send an email to make an appointment first. And in this course, we have 6 TAs. 3 of them are here. Zheng Yibing, Li Jing, and Li Renkun. So we have 3 of them here. They always are all in the 3rd floor of the Hosing Engineering Building, the ASIC Design Lab. And the email address are here. So this is the lecture information, you know it. So today, here, tomorrow we'll be in the how to call it? Well, I don't remember the full name. WMY. I try to change the room later because I want to use this Apple TV projection system. In that room, we don't have that. For tutorials, we have one fiction already. It's a Thursday, the noon session. And we are going to have another session, and the time will be determined later. And the TA has already sent an announcement to you to seek your available time. We'll try to find a common time for students who are not available for this time slot. Of course, website is on Blackboard. Let me ask how many of you have already checked the website? Please raise your hand. Okay, I think most of you have been there. So you see this set of lecture notes. The lecture notes, tutorial notes will be uploaded to the Blackboard system, homework and solutions also, and also some practicals. An announcement will be posted on the Blackboard. At the same time, it will be emailed to your CHK email account. So what is this course about? This course teaches the design methods for modern digital circuits. Digital circuit technology trends are described. Implementation methods and design flows for modern digital circuits are explained in details, and the trade-offs are discussed. Advanced circuit techniques in digital designs are introduced, and you will learn design tools, that is Verilog. And packaging and testing of digital integrated circuits are briefed. And you will gain practical opportunities in this course. You will build some digital design on FPGA boards. Let me take sample out here. So you will get a board like this. In the 4th week. So this is a FPGA design kit, a design board. And you will have 3 practical exercises to do, and you're going to use this board. The limited number of this this board is the reason that we have limited quota for this course. Here is the assessment scheme. The assignments, we have about 3 to 4 sets of assignment, written assignment, 10%, and 3 practicals, 20%, and then midterm tests, 20%. The tentative date is 20th October. In the lecture time, final 50%. So this is the course content, technology trends, implementation methods of digital circuits, design force, basically design force for 2 digital design methods, that's ASIC and FPGA. Then we spend quite a lot on very lot. And also a lot of time in design techniques with particular relevance to IC and FPGA. Last is about testing, a testing structure built in the IC. The course does not have a textbook, but we have a number of reference books. So these 3 are perhaps the most important textbooks. And we also have some other books, reference books. Learning outcomes of the course. So upon successful completion of this course, you should be able to understand the intricate trade-offs in different digital implementation methods, know with design flows, and have the competence to use some design tools. And use Verilog as the hardware description language, and apply advanced circuit techniques in digital designs, and gain a comprehensive knowledge of IC as a technology, and gain hands-on experience in implementing digital designs into hardware through practice. Basically, the practice through this board. This is the tentative course schedule. First week, we are and technology trends, and this will extend to next week, including IC digital circuit fabrication, implementation methods, around 1.5 weeks or 2 weeks, and then design flows. Then hardware description language, we focus on Verilog. I think for EE students, you learned the VHDL before. Verilog is similar, right? You learned the VHDL in your digital circuit system course. Final state machine. Design techniques with a particular reference to IC and FPGA, 2 weeks. And we will also show you an example of a simple microprocessor design in Verilog and testing. Finally, review. Now here I would like to make a special thank to Professor Oliver Choi, Emeritus Professor of the EE department, from whom the majority of the materials of this course is inherited. Okay, let's send things. It's about academic honesty. So university places a very high emphasis on academic honesty. So it takes a zero tolerance approach towards plagiarism, cheating, things like that. And there will be severe penalty for plagiarism. And this is a complete university style on academic honesty. You are encouraged to go through it. Okay, so that's about the course information. Any questions? Yes.
Well, the technology trends it involved in the midterm and final exam.
Yes, it will be. It could be tested. So everything taught could be tested. Thank you for your question. Any other questions? If no, let's start the first lecture. Start. Don't see the. I don't see this Zoom control bar here. I need to look from. Okay. Stop sharing. Okay, now I see the Zoom window. Anyway. We need to share the screen. See, there's no box. Yeah, I suppose the Zoom sharing is okay. No green box here. All right, anyway, let's move along. So first part of the course is about technology change of digital circuits. This is the content for this part, including the technology change, CMOS fabrication process, and nanometer lithography issues, nanometer technology nodes. And for the rest of today, we only have time to cover the first part, the technology change of digital circuits. So you can hear me at the back, right? Thank you. So before talking about the current technology change, let's take a look at the past history of the digital techniques. One in the past, digital technology, digital calculation could be carried out mechanically, not through electronic means. For example, this is a mechanical calculator. It's bulky, heavy, and slow. So why use electronics? Well, electronics are easy to move and control information. Basically, we don't control physical stuff. We control information, move and control information. And not things. So for example, the application of electronics, these applications, phones, fax, TV, the internet, etc. These things, we move information, we process information, we display and generate information. Because we are manipulating information, so it takes much less energy and cost than moving real things like this. So the electronic age arguably start about in about 1910, when Forrest, the scientist, invent the vacuum tube at that time. But electronics as an industry, we know it today, really started in when this event occurs, when this device were invented. So this is the transistor, I call it transistor. It was invented in 1948 by 3 engineers working for the Bell Lab. They are Brayton, Bardeen, and Shockley. So this is kind of solid state vacuum tube. The function of a device is similar to those of vacuum tube device, but it's in solid state. No vacuum inside, so it's much reliable. So although the electrical phenomenon was well known before the invention of those devices I mentioned, it was well known in the 19th century, and it was applied in telegraphy and telephone. But the discovery of electrons and the important formulation of important theory, quantum theory, happened much later. It happened in the early 20th century. And the pure stone theory for modern electronics is the quantum theory. It provides a foundation for the conduction of electrons in solid state materials, including metals and semiconductors. So that's the basis of solid state electronics. Without this theory, we could not enjoy the electronic devices we have today. So more than 100 years ago, people already invented and applied electronic devices, although electron had not been discovered yet. The first electronic device is used for rectification, like dial we use today. And rectification is a fundamental function we need in electronic devices. This device was discovered by Carl Brown in 1874, many years ago, before the formation of the atom theory, electrons, protons, things like that. So Carl Brown experimented with metal salt and found conductivity for this material in solid state. And the interesting thing he discovered is that the conductivity not only vary with the applied voltage, but also with the polarity. If you revert the polarity, you may see very little current. If you have another polarity, you see large current passing through the contact. And this phenomenon was particularly clear if one of the electrodes was a pointed wire. So in fact, he discovered the point contact rectifier effect without having the quantum theory. The theory for modern electronics was started in 1938 when Shockley created a theory that explained that rectification effect. I proposed this energy band diagram for solid materials, conduction band, valence band, Fermi level, things like that. That you for E students you learned in the 3210 in that course. Then here there is the birth of integrated circuits. Jack Kilby of Texas Instruments, this company, and Robert Noyce of Fairchild Semiconductor. They simultaneously invent the integrated circuits. They put a number of transistors on the same substrate to form a single piece of device. And that's the birth of integrated circuits. And then there is this famous law called the Moore's Law. Every one of you should have already heard of this law. Moore's Law. So this Moore, who is the co-founder of the Intel, he predicts the some phenomena. He predicted that a number of transistors put it on the state of the art integrated circuits would double about every year. And he put a lot of observation and prediction on his paper written in 1965. So basically, he put some existing data dots on a semi-log graph, and then make a prediction. He predicts that this trend will continue for many years. But later he modified that the doubling period is modified doubling period to 1.5 years instead of 1 year. And this prediction has been remarkably precise. And this exponential increase of transistor counts on IC has been valid in the past 50 years. And this is truly remarkable. Think about the chess problem. So in the international chess, there is a board, I think it's A by A square, A by A square. If you put a 1 rice on the first square, put 2 rice on the second square, and 4 rices on the third square. For each square, you double it. Then when you go through at the end of this 16th square, the amount of rises you get is huge. I think someone calculated it could fill between the sun and earth. So that's an example of exponential growth. And this Moore's law is an exponential growth effect. And it has been valid for the past 50 years. So this is truly remarkable. And so let's see some key milestones in the development of a digital processor, central processing unit, CPU. The first CPU or microprocessor is Intel's chip called modeled as 4004. This chip diagram is shown here. It contains a little more than 2,000 transistors. And it's a 4-bit processor. A 4-bit means the data size is 4-bit. So it was used in some simple controls, digital control system, and also in the calculators, digital calculators. The next milestone is an 8-bit processor by Intel called A0. More transistors were put on the chip. It's used for a first personal computer called ARTA, first personal computer. In that time, the computing power was was classified into a mainframe, mini computer, and personal computer. main thing occupies a large house. Personal computer smaller for personal use. And nowadays, personal computer is a dominant type of computer. So this is an 8-bit. Data size is 8-bit. Next milestone, Intel's A0, A6 processor, A0, A6 and A088 series. It's a 16 processor. More transistors were integrated. And it is the brain of the first IBM PC. You know, IBM PC becomes one of the most important computers, personal computers, very successful in the market. So lastly, this is first 16-bit PC, and lastly chip empowering the PC. Next milestone in the CPU development, CPU is a representative of digital circuits. Our next milestone is this A03A6 CPU by Intel. It's the world's first 32-bit processor, capable of multitasking. A single core. All these are single core CPUs. The next one, Pentium, a household name. Many more transistors are integrated on the chip than the previous one. Pentium is Intel's product, is a household name, and Pentium 1, 2, 3, all the way to Pentium 4. Pentium 4 contains 42 million transistors running at a clock rate of 1.5 gigahertz. But it's still a single core processor. Here is a table summarizing the evolution of the Intel's processor. This table is taken from one of the reference book here. This is the CPU name, the year of introduction into the market. This is clock frequency. Basically, see clock frequency increases exponentially in the early phases, but it saturates around 4 or 5 gigahertz. It won't increase furthermore, for a reason that we'll talk about later. And this column is the instruction set architecture. So 4-bit, 8-bit, 16-bit. The first one is 4-bit, then A00A is 8-bit, and A086 is 16-bit, and next generation is 32-bit. But starting from 32 bits, the name of this, the meaning of this bit changed. Previously, this ISA bit refers to the data size. But from 32-bit onwards, it refers to the address size. So a 32-bit CPU can handle only a certain amount of memory locations. It's 2 to the power 32. In terms of gigabyte, 2 to 32 bytes. 2 to 32 bytes. If I ask you to calculate, to convert it into gigabytes, how many gigabytes can it handle in terms of memory? How many gigabytes is it? 2 to the power 32 bytes. So 2 to the power 10 is 1K. 2 to the power 20 is 1 million. 1 M, not million. 2 to the power 30 is 1 giga. So 2 to the power 32 is 4 gigabyte. 4 gigabyte size. You see, it's very limited for today's use. Today memory at least 16 gigabytes for your laptop. But for this one is a 16 gigabytes. So the 16.4 this 64 ISA provides much larger memory space for the CPU to adjust. So actually, Itanium, this processed by Intel, Itanium 1 was the first 16-bit CPU. And later on, almost every modern day CPU are 64-bit type. And this is the process technology used. We have more details on this later. Basically, the first one use 10 microsecond, 10 micrometer technology, which means the metal wire width or transistor length has a minimum size of 10 micrometer. And this is keep shrinking. For Xeon, this server grade processor, was the first nanometer CPU. I mean, fabricated in 90 nanometer. Technology is below 100 nanometer. We call it nanometer technology. So this is the number of transistor counts. It increases exponentially, and that's the main technology trend. Here are a few examples of new processors. This is the Intel's Xeon E5 generation processor, introduced to the market in 2016 for server application servers, 64-bit ISA, contains 7.2 billion transistors. The size of the chip is about 500 millimeters squared. Clock rate is 2.2 gigahertz. It consumes 145 watts of power. The main difference of modern processor from those Pentium and before is that modern CPUs contains many cores, more than one core. So this one contains 22 cores. Any questions? It was fabricated in a 14 nanometer CMOS technology. This is another example, Intel Core i9. So for personal computer, introduced last year for desktop PCs, 64-bit ISA. It contains 16 cores, 8 high performance, which means high speed cores, and 8 efficiency cores, which means low power cores. So this is one core. You see some cores there. Clock rate is not much higher than previous generation. It's 3.2 gigahertz, but it can be turboed to 5.2 gigahertz. If you increase the clock rate, of course, the power consumption will be increased. The size is around 10 millimeter by 20 millimeter. It's fabricated in a process named as Intel 7. Intel 7 does not mean 7 nanometer. I will talk more about this later. This is from another company, Apple's A15 Bionic processor, introduced last year for mobile applications, smartphones or laptops. It supports 64-bit ISA, can run up to 3.2 gigahertz, contains 6 cores, 15 million of transistors. Size is about 100 millimeter squared. many cores, 6 CPU cores, and some graphic processing unit cores, GPU cores, fabricate in 5 nanometer CMOS technology. Okay, so that's some technology change illustrated by the example of Intel CPU. Now here we have a more comprehensive data on the technology chain. This chart is taken from this source. It's about transistors count in state-of-the-art microprocessors. And the y-axis is the number of processors per chip. The horizontal axis is the year of the first introduction to the market. You see, for the 4004, Intel's first, the world's first processor chip here, number of transistors is slightly above 2000. Then this Intel's 486 is the first one that has greater than 1 million transistors. So it's called VLSI chips. If a chip contains more than 1 million transistors, it's called a very large scale integration, VLSI. This Pentium 3 processor by Intel contains transistors more than 10 million. And this one, Pentium 4, Pentium 4 one model here, contains more than 100 million transistors. Then this is 1 billion. The number of transistors is huge. Now, also chips from other brands. So that's the key technology chain. It's the transistor count in the state-of-the-art digital processors. It keeps increasing. The trend is about doubling every 2 years. Now, it doubles every 2 years. Transistor count doubles every 2 years. That's the big trend, major trend. So when you have more transistors, you can do more functions. And this transistor count, that trend, is enabled by this feature size reduction. We can make a transistor to be smaller and smaller. So every 2 years, every 2 to 3 years, we get a new generation of fabrication technology. So feature size, the classical definition of feature size is the length of a transistor, the gate length of a transistor. Gate length transistor, you learned it before, right? There is a gate from the source to the drain. There's a gate above it. The length of the gate is called the gate length. So the feature size basically refers to that, all the metal length, metal width. The feature size shrinks by 30% in every new generation, 2 to 3 years. So here is the time scale, the year. This is a transistor critical dimension. First one is 10 micrometer technology. It shrinks down. Y-axis is the log scale. Say this is 0.8 micrometer. Or say let's look at this one, 0.18 micrometer. The next generation is 0.18 multiplied by 0.7. It's a reduction of 30% in length. So the length in every generation is reduced by 30%. This is about 70% of the original size of older generation. If you consider 2 dimension, it's 0.7 by 0.7 is 0.5. So in every generation, the size is reduced by a half. In other words, the density, the number of transistors per area, doubles in every generation. So that's the transistor density chain. This is a relative density. This is the year. Different colors refers to different digital ICs. For microprocessors, it's in the blue diamond-shaped dot. You see the trend is exponential and doubles roughly about every 2 years. And also some other trends, say density in the static RAMs and in memory, static RAM is a red dot. Same trend, doubles every 2 years. For logic gates, it doubles every 2 years. A similar trend, basically double the density doubles every trend. So this is not the same as transistor count. Is the density as the number of transistors per unit area. It's not number of transistors per chip. It's the density. You can make the chip larger to contain more transistors. And so there's 2 ways to increase the number of transistors per chip. One is to increase the transistor density. The other is to make a larger chip for the transistor, larger total area. And actually, there is a direction going that way. But the key benefit from this scaling effect is the reduction of the transistor's cost, or the cost per transistor. Moore's original paper stated that the cost per component, cost per transistor reduces. This 1962's cost. And this is a different level of integration. If you look at the minimum level here, the cost reduces from generation to generation. And this is a more complete. This is original data in the original paper. This just contains data up to year 2001. This is a cost per transistor in terms of US dollar. This is $10 per transistor, $1 per transistor. In year 2000, the cost per transistor is $1 millionth dollar. Then, so basically, in modern days, if you talk about transistor cost, it's almost free. So when you design a digital IC, say you want, say, 10,000 more transistors, right? It almost comes free. Of course, the whole chip is not free because it contains so many transistors. Okay, I think the time's up. I will stop it here. Okay, any questions? If no, let's continue tomorrow. Thank you for coming. See you tomorrow.